this video, I will be briefing stellar evolution. Stellar evolution is the life cycle and formation of stars. Stars are one of the most widely recognized astronomical objects. These are balls of condensed dust and gas that glow as a result of nuclear fusion. Many people think that the space is a vacuum. There is actually a lot of dust and gas particles floating through space in very low densities. These are called interstellar mediums. They consist of 99% gas and about 75% being hydrogen and the rest being helium. The more denser areas of these mediums are known as giant molecular clouds, which is more commonly known as nebulae. They have heavier molecules such as water, carbon monoxide, methanol, and ammonia. The three main types of nebulae that stars form from are emission nebulae, the reflection nebulae, and the dark nebulae. Emission nebulae emit their own radiation as a result of ion and electron interactions. Reflection nebulae reflect radiation from nearby sources. The dust particles in the nebulae scatter and polarize light. Dark nebulae absorb and scatter radiation. They appear as black splotches in the sky, making them hard to see. In nebulae, gravitational force pulls together particles and molecules into dense clumps. As these clumps get bigger, they trap more thermal energy, causing the core of this clump to rise in temperature. Gravitational potential energy is converted into thermal energy, which causes the star to compress further. This increases the surface temperature of the star, making the star glow. And voila, a star is born. Protostars are generally detected by electromagnetic radiation, as other astronomical objects and particles obstruct our view of the star. While forming, the protostar begins to spin. Along with this, the cloud around the star spins too. This is called an exertion disk. These disks shoot out narrow jets of dust and molecules through its magnetic poles. As the core of the protostar reaches a certain temperature, nuclear fusion begins. Fusion is a type of nuclear reaction that fuses two nuclei to create a heavier element or isotope. The temperature in the core of the star is high enough to split hydrogen and helium atoms into electrons and positively charged ions. In nuclear fusion, mass that is lost is compensated by energy, which relates to Einstein's famous formula E=mc². The type of fusion in the star depends on the size and the mass of the star. There are three types of fusion: proton-proton fusion, helium fusion, and carbon cycle fusion. Proton-proton fusion starts with two protons fusing. It results in a proton and a neutron, which creates deuterium, which is heavy hydrogen. Deuterium fuses with another proton, which results in helium-3. The helium-3 fuses with a proton to create two helium nuclei. These two nuclei fuse to create an alpha particle, which is also a helium atom, and release two protons as a form of energy. In helium, or the triple alpha fusion, it fuses to the alpha particle, like how it did in the proton-proton fusion. Two of the alpha particles fuse to leave us with a helium nucleus and a beryllium-8. These two fuse together to form carbon-12. In carbon cycle fusion, particles fuse to form carbon-12, like previously. When this carbon-12 fuses with a proton, it results in a nitrogen-13. This also decays a proton, which emits a positron and a neutrino to form carbon-13. Carbon-13 captures a proton to create nitrogen-14. Nitrogen-14 then captures another proton to become oxygen-15. Oxygen-15 and a proton fuse together to result in oxygen-16. Oxygen-16 emits an alpha particle to become carbon-12. This process goes in a cycle. Equilibrium in stars refer to the state of stability. Nuclear fusion produces energy which exerts outwards, while gravitational force exerts force inwards from the outside of the star. This ensures that the star doesn't collapse or explode. Stars have different luminosities and temperatures, and most of the time, they are categorized using this. The Hertzsprung-Russell diagram helps us determine the evolutionary sequence of stars, graphing the star's temperature against its luminosity or its color against its absolute magnitude. After living through millions and billions of years, stars eventually run out of hydrogen, which stops fusion. This is where most stars die. Smaller stars die a more gentle death, while larger stars die a more explosive death. The most common deaths in stars are supernovae, white dwarfs, neutron stars, black holes, and red giants. Supernovae is an explosion of a star. When fusion stops, the core of the star becomes very dense. So dense that the star won't be able to withstand its own gravitational force, resulting in an explosion. White dwarfs are formed at the end of nuclear fusion in the stars. They start ejecting their outer layers into space, leaving behind a very hot core and a planetary nebula. The core becomes a white dwarf, and the temperatures of this dwarf can go over 100,000 Kelvin. Neutron stars are formed when the star collapses in on themselves. Remember equilibrium in stars? As nuclear fusion stops, the core stops producing energy, which means that gravity will take over. Gravity compresses these stars so much that the distance around the star only measures 20 kilometers. A sugar cube chipped off of the star can weigh as heavy as a mountain here on Earth. There are two main types of neutron stars, pulsar stars and magnetar stars. Pulsar stars emit radiation from both of its magnetic poles. They also spin incredibly fast, with a rotation being 0.9 seconds. When the radiation comes in line with the Earth, we see it, which creates a pulsing effect, hence its name. Magnetar stars have a very strong magnetic field. Neutron stars have a magnetic field that is 1 trillion times the field here on Earth. In magnetars, however, the magnetic field is another additional 1,000 times stronger. These guys rotate anywhere from 100 to 1,000 times in a single second. As the crust of the star holds a lot of pressure, even the slightest of disturbance can cause a massive explosion. Stellar black holes form in a similar way to the neutron stars, but the stars that are collapsing have a higher mass. The star keeps collapsing until all of the matter is condensed into a single point in space, known as the singularity. The gravitational pull is so strong here that even light cannot escape a certain radius around it. These holes bend time and space around it, changing the behavior of matter. What happens if you go into one of these holes still remain a mystery. Red giants are formed from a collapse in a star. When fusion stops, the star begins to collapse in on itself. This process converts gravitational potential energy into thermal energy. This temperature rise will reach the outer shell of the core, which is made out of hydrogen. When the temperature is high enough, nuclear fusion starts again. This causes the outer layer of the star to expand, which also cools the surface, giving it its red appearance. So that's stellar evolution for you. Thank you for listening.